Assalamu alaikum dear students. I welcome you to 36th lecture of probability and stochastic processes. In previous lectures, we were discussing Markov chains. In today's lecture, we'll continue with our discussion of Markov chain. We'll revise what we covered in previous 2 or 3 lectures and build on top of what we have already covered to expand our knowledge of Markov chains. To review what we have already covered, Markov chains represent a special subset of stochastic processes. And stochastic processes are collection of random variables with a sense of time, with orderliness in time. This type of collection of random variables can be assigned a timestamp. There is a first random variable, a second random variable, a third random variable, and so on and so forth. And these first, second, third random variables realize their values one after the other in time. This is applicable if we have a finite number of random variables or a countably infinite collection. If we have an uncountably infinite collection, even then we can place a sense of time orderliness, but you cannot call them first, second, third. There is a huge collection and you can just see 2 random variables and see which one of those 2 realizes its value first and which one realizes its value later. We'll talk about these uncountably infinite collection of random variables later in this course. In Markov chains, we discussed a few examples, and I tried to bring to this course examples which are interesting, challenging, expandable, and examples that we can relate to. For example, an interesting and unique, as far as a Pakistani perspective is concerned, a unique example was discussed of a person who aspires to perform Hajj but has to go through a sequence of unpredictable events. First was whether he can afford, will he apply for Hajj. The second was if his application is going to come up in a random draw. And the third was once his application is accepted, is he actually going to perform Hajj or is he going to not perform Hajj because of some unfortunate, unforeseen outcome in his life. So this real life unique situation was modeled as a time sequence of observations of status of a person who aspires to perform Hajj. We model this real life situation and its sequence of unpredictable outcomes with a simple Markov chain. In the beginning, we used only 4 states, and probabilities of transitions from different states to other states was chosen to reflect that simple model. Let's have a look at that model quickly and move beyond this simple model. In this simple model, this state represents where a person has not applied for Hajj, this represents when he has applied, and this represents when his application has been approved, and this represents when he has performed Hajj. All these transitions, particularly this transition of one probability where a person who has performed Hajj remains in this state, he never goes back to this state, never applies for Hajj again, and his application does not go through the random draw process. So this simple model was used to highlight this real life situation. When we took an initial probability distribution of 1, 0, 0, 0, that is when we start our observation, the person always starts in this state where he has not yet applied for Hajj. He may apply with a probability of 0.1 or he may wait another year with probability of 0.9. Starting with this initial probability distribution, we saw that the third probability distribution, the probability distribution after 3 observation times was given here. Probability distribution after 100 times was shown here, and this shows that if a person starts in state 0 with 100% probability, after 100 observation intervals, he has 99.69% probability that he has reached state 3. That is, he has performed Hajj. And if you just continue applying this recursive observations, then you see that in the limit pi infinity or long-term probability distribution of this Markov chain is 0,001, that eventually there is 100% probability that the person has performed Hajj. So if he starts with 100% probability here, eventually he will reach here with 100% probability, and once he reaches here, he is going to stay here. This is an absorbing state. So with this simple model, we talked about a real life situation and analyzed it and looked at different aspects of this problem, different probabilistic analysis of this problem, and found that for this sequence of random variables, which are observations of status of a person who aspires to perform Hajj, behaves in a certain way that eventually that person is going to be found in state 3. That is, eventually in the long run, we will find this Markov chain to be occupying state 3, or the status of an ordinary person who aspires to perform Hajj and repeatedly applies for Hajj will be that he has performed Hajj. There were some shortcomings in this model. Particularly, we knew that these transitions should have been at a well-defined times in the year, because there is only one time in a year that a person can apply, and there is only one time a year when the transition from being applied for the Hajj or being accepted for the Hajj takes place, when the random draw is held. And similarly, there is only one instance in time when the Hajj is actually performed. But this Markov chain showed that a person can apply for Hajj for every transition. We expanded this model so that we can model this situation of being able to apply for Hajj only once in a year. And the expanded model looks like what is being shown on your screen. In this expanded model, we have introduced two more states, state 4 and 5, and if a person applies for Hajj, he goes through possibly this sequence of states from 0 to 1, from 1 to 2, from 2 to 3, or from 0 to 1, from 1 to 5, and then back to 0, or from 0 to 1, 1 to 2, and back to 0. So this expansion of state 0 into state 0, 4, 5 reflects our desire to model this situation where a person only applies for Hajj during one particular observation instance in a year. In other two observation instances, he is in these dummy states, either 4 or 5. When we analyze this Markov chain and looked at its initial probability distribution and probability distributions at later observation instances, we found that this Markov chain also behaves in the similar manner. There was one difference, that the observation times were assumed to be 3 in 1 year, and if we observe this status of a person on every 3rd, 6th and 9th observation times, we see a very nice expression, and we saw that probability distributions at later sampling intervals showed a behavior which was similar to previous case. That is, if a person starts with probability 1 in state 0, that is, he has not applied for Hajj, and you keep on going from state 0 to state 3 to state 6 to state 9 and reach state 150, which is 50 years after the first opportunity for applying Hajj, you see that at 150th observation instance, probability of that person being in the initial state is less than 5%, and probability of that person having performed Hajj is more than 95%. And if you take this sequence of observations to infinity, just for the sake of argument, you see that eventually probability of that person having performed Hajj being in state 3 is 1. So the behavior of this Markov chain is very similar to the previous Markov chain, because a person who starts in state 0 with 100% probability eventually reaches state 3, which is that he has performed Hajj, and he reaches at this stage with 100% probability in the long run. If we look at the expanded Markov chain, then you can see that by introducing these two dummy states, we have put a more precise meaning to the observation instances. Now the observation instances are 3 in 1 year, and a person can apply for Hajj only one of those instances. His application goes through or is rejected on the next observation instance, and he performs Hajj or goes back to the population which has not performed Hajj on the third observation instance. But if you look at this loop where he stays in state 3 with probability 1, this happens 3 times in a year. But since this is a self-addressing loop, a person stays here with probability 1, this is the only thing that's going to happen. It can happen once a year or 3 times a year. It does not make any difference. This expanded Markov chain was used to model a situation where if a person has performed Hajj, he is not allowed to reapply. In real life, if a person has performed Hajj and he has waited for at least 5 years, he can reapply. Let's try to model this reapplication scenario. And if we want to keep the things simple, we'll assume that a person is allowed to reapply for Hajj as soon as he has performed it. But all the people who has performed Hajj will not reapply. Some will stay there and some will reapply and join the population in that same process where their application goes through a random draw and all these other steps. This situation was modeled with this Markov chain, which you can see on your screen. So if a person has reached state 3, he is going to stay in that state with probability of 95%, and with a probability of 5%, he is going to move to state 1 on next observation interval. And here his application is in, and if his application goes through, it's accepted, he moves to state 2, otherwise he moves to state 5. We discovered that there is a problem with this model, because this self-referring loop is going to happen on all observation instances 3 times a year. So if he has performed Hajj and he has applied for Hajj, on the next transition he'll move here or he will move here. That is not allowed. He is going to be allowed to apply for another Hajj on 1 instance per year. So this state needs to be expanded for this particular case where he is allowed to reapply. So that expanded state is shown on your screen now, where we have introduced dummy states 6 and 7. So if a person has performed Hajj, he is in state 3, he either applies with all other people who has not yet applied and moves to state 1, or moves to state 6, which represents that he has performed Hajj but has not reapplied. When the random draw takes place, this person joins other people who have applied for Hajj and moves to either state 2 or state 5. And those people who did not reapply simply move to a dummy state 7. The people whose applications go through perform Hajj and move to state 3, and these people who had performed Hajj but did not reapply simply move back to state 3. In the first year, when we start observing people starting from state here, after 1 year there will be some people who had performed Hajj and other people stay back. But starting from the second year, people that we found in state 3 are a mixture of people. Some have performed Hajj for the first time and they move through this idle loop and come back here. Some people reach this state for the first time because they start from this state because their applications got rejected. And some people who are very lucky go through this loop where after performing their first Hajj, they reapply, their application is accepted, they move to state 2 and then come back to state 3 after performing 2 Hajjs. Similarly, at the 9th sampling instance, people will be in this state, but this will be a mixture of people. Some had performed only 1 Hajj, some had performed 2 Hajjs, and few very lucky ones, very few, had performed 3 Hajjs. So because there is an interesting difference in this model and the model we saw previously. Previously, in the 2 models that we saw, state 3 was an absorbing state. Once a person reaches state 3, he remains in state 3. But now state 3 is not an absorbing state. If a person has reached state 3, he can remain in state 3 if he decides not to reapply. But if he decides with non-zero probability, even though small, 5%, he moves back to state 1 and joins rest of the public. If you want to analyze this Markov chain to see the long-term probability distributions starting with a particular distribution, for example, 1, 0, 0, 0, 0, 0, 0, 0, that is starting with 100% probability in state 0. If we take that starting probability distribution and apply the transition matrix of this Markov chain and go towards infinity and observe this Markov chain in the long run at time instances which are divisible by 3, you will see that this is the scenario that you get. In the long run, for those sampling instances that are divisible by 3, you will see that people are either in state 0 or in state 3. People who are in state 3 have performed a Hajj, either 1, 2, 3 or more than 3. And people who are observed in state 3 did not apply for Hajj, but they could be people who have performed Hajj, reapplied, and then their application got rejected and then they moved to state 0. Or they reapplied, their application was accepted, but they could not go for another visit due to some unfortunate circumstances. So if people are in state 0, it does not mean that they have not performed Hajj at all. It's quite possible that people in state 0 have performed 1, 2 or multiple Hajjs. But people in state 3 are purely those people who have performed at least 1 Hajj. And probability of a certain person being observed in state 0 is 25.47%. And probability of a certain person being observed in state 3 is 74.53%. So in the long run, when this Markov chain has settled down and the effects of initial distribution have faded away, there is approximately 1/4 a chance that a person is found in state 0, where he may have performed Hajj or even more than 1 Hajj, or he may have not performed Hajj at all. And there is a 3/4 chance that we'll find a person in state 3. If you observe this Markov chain at instances which are not divisible by 3 but give a remainder of 1, then we see that we can find this scenario where people are observed either in state 1 or state 4 or state 6. This is logical because people who were previously in state 0 either move to state 1 by applying for Hajj or move to state 4 by not applying for Hajj. Similarly, people who have performed Hajj either move to state 1 by reapplying or state 6 by not reapplying. And when things have settled down, probability of you seeing a person in state 1 is about 6%, seeing a person in state 4 is about 23%, and seeing a person in state 6 is about 71%. And if you observe things at next sampling interval, you can find people in state 2, 5, or 7, and corresponding probabilities of observing a certain person in state 2, 5, and 7 are given as 3.76%, 25.43%, and 70.8%. So this Markov chain does not have an absorbing state. Things keep on moving from one state to the other, and in the long run you see this Markov chain in a periodic behavior where if you observe it at a sampling instance that is divisible by 3, you see that people are found in just 2 states. If you observe at next instance, they are found in 3 other states, and if you observe at next instance, they were observed in other remaining 3 states. So this Markov chain does not have an absorbing state, and there is no state which becomes the destination of all people as the things continue to evolve. There is another interesting concept that should be introduced at this level. If you see the model of this expanded Markov chain, you observe that all states are reachable from all states. That is, a person can be observed in any state at the start of our observation, and he has a chance of moving to all other states. Even if he starts in state 3, there is a positive probability that he will reapply and move to this set of state. He will move to 1, and if his application is accepted, he will move to 2. If it is rejected, he will move to 5. Next year, he will move to 0, and then he will either move to 1 or to 4 and 5 again. You can look at this expanded model of this Markov chain and convince yourself that all states are reachable from all states eventually. That is, you can start from any state and keep on moving from one state to another, and eventually you will hit a destination state. This was not true in the previous 2 models. If we start in state 3, you cannot of course start in state 3. You start in state 0, move to state 3, and we start our observation at a delayed sampling instance when we find that person in state 3. If he is in state 3, he is not going to move to state 0 or 1 or 2 because he is not allowed to reapply for Hajj. But in this expanded model where a person who has just performed Hajj is allowed to reapply for Hajj, and chances of him doing that is 5%, and with 95% probability he stays in that loop where he remains a Haji and does not apply for another Hajj. This concept of reachability will be expanded upon later, but for now the interesting idea is that if you have an absorbing state, you somehow reach there, then from that absorbing state it's impossible to reach other states. But if there are no absorbing states, they are transient states, states which allow you to move out of. So if a state is absorbing state, it does not allow you to move out of it. But if state is a transient state, it allows you to move out of that state. So if states are transient, like this case, you can start your observation instance anytime where a person is in a particular state, and he will eventually reach other states. We'll classify states in terms of absorbing states, transient states, and other type recurrent state shortly, probably towards the end of this lecture. But from this expanded model, it's obvious that if you allow a Haji to reapply for another Hajj, he can move from any state to any state. All states are reachable from all other states. By changing the nature of state 3 through this procedure where a Haji is allowed to reapply for another Hajj, we have transformed the behavior of this new Markov chain. By changing the state 3 from an absorbing state to a transient state, now probabilities are different. This has some practical consequences also. If a person has performed Hajj, he may reapply, but he should not be considered part of the crowd who applies for Hajj for the first time. He is a different category. So we are going to duplicate the application procedure for people who have already performed Hajj. This expanded Markov chain is shown on your screen now. And you can see that this has 11 states because we started from a simple Markov chain and expanded in a step-by-step manner. I hope that you will be able to make sense out of all these states. Of course, state 0, 1, 2, 3, 6, 7, 4, 5 are previous states. But there are 3 additional states, 8, 9 and 10. So look what happens if a person performs Hajj. He moves from state 2 to state 3. And this happens with 99% probability. And this is applicable to people who perform Hajj for the first time. They start from this state 0, go through the application process, their application is accepted, and then they perform Hajj and move to state 3. Now, state 9 is a new state which represents that a person who has performed Hajj reapplies for Hajj. If he does not reapply for Hajj, he moves to this state 6 with 95% probability. So from state 3, if a person has performed Hajj, he moves to either state 9 or to state 6. From state 9, he either moves to state 10, which implies that his application is accepted, or he moves to state 7 with 40% probability, which means that his application was rejected. If his application is accepted, he performs another Hajj with 99% probability, and with 1% probability, he moves to this state 8, where he fails to perform Hajj even though his application was accepted. This state 8 represents people who have performed Hajj, but they are waiting for their next opportunity to apply for Hajj, and which is going to happen when they move from state 8 to 9. A person can reach state 8 after performing Hajj when his application is accepted, but he could not go. Or a person who has performed Hajj does not reapply and moves to state 6, then moves to state 7 with probability 1 because he is waiting for other things to happen, and then he moves from state 7 to state 8 with probability 1. I have changed this scenario from that scenario. If a person is in state 8, he could have reached through this path or through this path, and he is going to either reapply for Hajj, moving to state 9, or not apply for Hajj and go to state 6. Probabilities of these two transitions are 0.2 and 0.8. So if a person belongs to this right side group, he has performed at least one Hajj and he reaches this state, then there is a stronger probability, 0.2, compared to this probability of 0.1. So people who have performed Hajj have a stronger probability to apply for another Hajj than people who never applied for Hajj. So with this slight change, this is the expanded model of a Markov chain representing a real life situation where people apply for Hajj, their application goes through a random process, and then they perform Hajj. Once they perform Hajj, they can reapply immediately, or they can choose not to apply and move in this loop. If they decide never to apply for another Hajj, they will move from state 3 to state 6 to 7 to 8, and then again to state 6, 7, 8. So this state 6, 7, 8 is an idle loop where a person who has performed Hajj does not reapply for it. By duplicating the application procedure for people who have already performed at least one Hajj, we have divided this Markov chain into two distinct parts. The left side part consists of states 0, 1, 2, 4, 5, and right side part consists of states 3, 6, 7, 8, 9, and 10. People who start in state 0, they can move to state 3 in first attempt, that is, when the third sampling interval happens, or they can stay back due to certain reasons and move to state 3 in sixth sampling instance. They can move to state 3 in later instances which are divisible by 3. But once they move to this state, they never go back. Does it mean this state 3 is an absorbing state? No. From an absorbing state, you cannot go anywhere. You come back again and again with probability 1. This is not the case here. You can certainly go from state 3 to either state 6 or state 9. But this group of states, the right-hand group, represents an absorbing subset of state space. If all 11 states are the state space of this Markov chain, then this right side set, the subset, is an absorbing subset. Once you hit any one of these states, you cannot go back. So if you start in this group and reach here, there is no way you can go back. So in terms of reachability, all states in the right-hand group are accessible from all states in left-hand group. But once you are in the right-hand group, you keep on moving from different states to different states, and hence all right-hand states are accessible from right-hand states. When you combine the two observations, you say that states in this right side subset are accessible from all states. They are reachable from all states. But these states on the left side group are not reachable from the states in the right side subset. You can make other interesting observations and analyze this well-expanded Markov chain in terms of its asymptotic behavior, in terms of its long-term behavior. And you can start with an initial distribution which is a meaningful one, that is, a person starts in state 0 with 100% probability. And then you observe at sampling instances which are divisible by 3. If you continue to do that, then every sampling instance that is divisible by 3 represents 1 year of observations. So you can observe this Markov chain for status of an ordinary person who starts in state 0 year after year after year. I have tabulated some of these probability distributions, starting with the initial distribution of 1, 0, 0, 0, 0, 0. That is 1 in state 0 and then zeros for all states. If you start with that probability distribution and observe the status of this Markov chain at third sampling instance, you get pi 3. So pi 3 is probability distribution at the third sampling instance, and you see that probability of finding a person in state 0 is 94%, and finding a person in state 3 is almost 6%. So if you start in state 0 with 100% probability, next year you will be in state 0 with 94% probability, and you had performed Hajj with probability of approximately 6%. By the time of sixth sampling instance, that is the second year, we observe a probability distribution which is pi 6, and pi 6 shows that there is an 88.47% probability that a person who started in state 0 is still in state 0, there is a 5.76% probability that person has performed Hajj, and this includes the case where he has performed 2 Hajjs. And there is a probability of 5.76% that a person has performed Hajj but has decided not to reapply for another one. If you keep on doing that, then you will see that in pi 9, when the 9th sampling instance occurs, probability of finding a person in state 0 is 83%, finding a person in state 3 is 6%, and finding a person in state 8 is 10.67%. Let's make a jump and observe the situation at 30th sampling instance, that is 10 years after we start making an observation, and our start was that a person we started observing was in state 0 with 100% probability. This situation is captured in pi 30. So by the time 10th year is upon us, we see that the person will be in state 0 with a probability of 54.21%. He will be in state 3 with a probability of 7.78%, and he will be in state 8 with a probability of 38.01%. So the person has performed either one or multiple Hajjs, and he has just performed a Hajj with a probability of 7.78%, or he has performed one or more than one Hajj and he is in state 8 with 38% probability. Let's make a really big jump, a theoretical one. We observe this Markov chain at 50th year, at 150th sampling instance, and observe what we see at pi 150. You see that a person who starts in state 0 with 100% probability is still in state 0 with a probability of 4.68%. He is in state 3 with probability of 10.64%, and he is in state 8 with 84.68%. And if we observe the situation after 100 years, probability of finding that person in state 0 is less than 1%, it is 0.22%. And probability of finding him in state 3, that is, he has just performed a Hajj, either first one or after many previous Hajjs, is 10.9%. And probability of him being in a state where he has performed Hajj and did not reapply is 88.89%. If we take asymptotic behavior and take things to very large indices, then if the sampling instance is divisible by 3, we observe pi 3k, where k is an integer. In that case, there is a probability of 0 that person will be in state 0, that eventually the person has performed Hajj. And he will be observed in state 3 with probability of 10.91%, and he will be observed in other state, state 8, with 89.09%, which represent people who have performed one or more Hajj and they have not reapplied in previous year. And if we observe this Markov chain at other instances which are not divisible by 3, we observe them in other states. Let's have a look at graphical representation of situation that we see in the long run. In the long run, if we observe a person, we observe him either in state 3 or state 8. He has performed Hajj eventually, and with around 11% probability we'll see him here that he has performed Hajj recently in the previous attempt, and in state 8 where he did perform Hajj 2 years or earlier and did not reapply in the immediately preceding year. If we observe this Markov chain at next sampling interval, then people have moved to either state 6 or state 9. If they were in state 3, they reapply and move to state 9. And if they don't reapply, they move to state 6. And if they were in state 8, then they decide to reapply after a gap of certain number of years and move to state 9, and they decide not to reapply again and move to state 6. At next sampling instance, they move to either state 7 or state 10. If they were in state 9, where they had applied for another Hajj, they move to state 10 with 60% probability because their application is accepted. Or if their application is rejected with 40% probability, they move to state 7. If they had not applied, then they simply move to state 7. And of course, at the next sampling instance, where it is again divisible by 3, you will find people either in state 8 or in state 3. State 3 represents people moving from state 10 to state 3 by performing Hajj, or moving to state 8 by not performing Hajj, or simply moving from state 7 to state 8. As you can observe from this sequence of 3 slides, that in the long run, you find this Markov chain in either state 3 or 8, or state 6 and 9, or state 7 and 10. In the long run, the Markov chain is not found to be in any of the states on the left hand side. So long-term distributions of probability are only going to be non-zero for these states in the right hand. If we look at that collection of probability distributions, you should observe the last 3 lines very carefully. You can see that in the long run, if the sampling instance is divisible by 3, you find non-zero probability in state 3 and 8, or other pairs of state as shown by the lines representing probability distribution at sampling instance 3k plus 1 or 3k plus 2. So this subset of 6 states represents those states where eventually you will find a person, and the set of states in the left side subset are states where eventually you will not find a person. This expanded model of real life situation representing performing of Hajj is quite complicated. It has 11 states and a complicated transition matrix, but you can appreciate that it is closer to real life situation. And by observing the transition matrix, the initial distribution and subsequent distributions, you can get a feel of the process through which this sequence of unpredictable events unfold. And a person who has not performed Hajj at all goes through some unpredictable events and performs Hajj, and then he performs multiple Hajjs. In this model, we divided the states into 2 subsets. One was on the left side, where person usually starts, moves around, and then jumps to the right hand subset by moving to state 3, that is by performing Hajj. Once he is in state 3, he moves around into the right hand set, applies for another Hajj, either succeeds or does not, but he remains in that set, which represents people who have performed at least one Hajj. We talked about reachability, we talked about absorbing states, but in this case, none of the state is an absorbing state, but they are behaving differently. If we start from any state in the left side subset, we move out of it after a few transitions. That few could be 5, 10, or if you really want to imagine long-term sequence of failures, it could be 50, 100. But eventually you move to right hand subset. and once you are there, you remain there and keep on moving. So if this Markov chain was allowed to behave the way it is modeled for infinite number of sampling instances, the states in left side are going to behave differently than the states in the right side. The state in the left subset are called transient states because if you start there, you have a positive probability of moving to other states and then not coming back, and this is going to happen in finite number of transitions. And the states in the right hand subsets are called recurrent states. Once you are in any one of those states, you will come back to that state. You will jump around, perform Hajj, reapply, not reapply, but if you are in any of those states in the right hand subset, you will revisit that state after a few steps or after multiple steps. But it's not possible for you to not visit those states in the right hand subset. So when studying Markov chains, we divide states based on their behavior, usually their long-term behavior. If the model is allowed to evolve, even though in the case of Hajj, if a person is young and applies, we can only observe his status for 30, 40, 50, maybe 60 or 70 years. But the model is usually allowed to evolve for infinite instances of time, and then we observe the behavior of different states and classify different states according to that behavior. Let's start a formal process of classifying different states of a Markov chain based on their behavior. Before we do this classification, we have to have some definitions so that we know how things are represented. The first definition that you see on your screen represents a way to define probabilities of events in terms of the starting value of the Markov chain. If the Markov chain starts with random variable capital X0 and it has a value small x with other random variables capital X1, X2, X3, assuming corresponding values of small x1, x2, x3, etc., then this event and its probability can be denoted by P with subscript x and then writing random variables other than the starting one. So Px, x1 being equal to small x1, random variable x2 being equal to small x2, etc., is equivalent to probability of event where capital X0 assumes this value, which is the subscript of this notation. So this is just a different way of writing probabilities of events in terms of the starting value of Markov chain. The second definition that you can see on your screen is definition of number of visits, usually denoted by capital N and then y in brackets. This represents number of times we observe this Markov chain in state y. So if we have a Markov chain which is represented by a collection of random variables capital Xn and has a corresponding state space represented by set S, then ny is number of times this Markov chain is found to attain value of y. Y is one of the values in state space set S. The third definition that you see on your screen is expected value of any random variable given that the Markov chain starts in state X. So if Markov chain starts in any particular state X, we put that as subscript and we find the expected value of any random variable that we are interested in. The next definition is definition of hitting time. If we have a Markov chain represented with a collection of random variables capital Xn and it has a sample space S, Then we take a subset of this sample space and call it A. And hitting time of this subset TA is the first time that we will observe the Markov chain to belong to this subset. If subset has certain number of states, the first time any of those states is visited is the hitting time of that subset. And the last definition is of reachability. Reachability is a probability. It is represented by rho xy, and rho xy represents the probability of this Markov chain starting at state x and reaching at state y at any subsequent time. That time could be very far away. If it ever reaches state y, and this happens with a certain probability, we say that this is the reachability. This probability is given a special name, reachability. If state y is never reached, then this probability is 0. So if you want to classify states of a Markov chain based on their behavior, then the first type of state is an absorbing state. It's a special state with one-step transition probability of 1. Once you are in state x, the next time you are observed, you will be in state x, and next time, and next time. Once you are in state x, you cannot get out. You are always in that state on subsequent observation instances. A recurrent state is visited repeatedly again and again, and reachability, that is probability of starting from state x and coming back to that state x, revisit to that state x in finite number of steps, no matter how many, is 1. If you have visited this state now, you will visit again in finite number of steps. So recurrent state is a state which is visited repeatedly again and again. On the other hand, transient state is visited only finite number of times. If you have visited it a few times, finite number of times, then there is a non-zero probability that you will not revisit it again. So rho xx, that is reachability, is less than 1. With this initial classification that I have given you, I have to stop my lecture because we are running out of time. But in subsequent lectures, we are going to formally use probabilistic tools to find these expressions of reachability, hitting times, and number of times a state is visited to classify different states of a Markov chain. Till then, I wish you the best. Thank you. Khuda Hafiz.